Okay, I think we're ready to go. Let's go together, floor.
Thank you. Thank you. Okay, so this is part 2, continuing from yesterday, where we sort of introduced the idea of metropolis Hastings, and then more generally, Markov chains on general state spaces. Something we did yesterday was we sort of discussed sufficient conditions for when we don't have to worry about convergence of the metropolis Hastings algorithm. And one of the reasons we did that yesterday was just to ensure that for most sensible target densities that arise from practitioners, unless they're in some very restricted region or something else is going on, if they're on RD, and if I define a proposal density that is also defined on RD and has positive support on RD, then almost always I don't have to worry about whether the Markov chain will converge or not. And so those type of questions I'm not going to worry about. Unless, of course, we are given a target density where we need to be really, really careful. Okay, but so the idea of convergence itself, we're not going to worry about because it will almost automatically be granted by the definition of the problem and the choice of our proposals. Okay, so here today we'll talk about gradient-based proposals, and then on Thursday, the part 3, I'm going to then talk about almost gradient-based proposals for situations where gradients may not be available. And so this is sort of the background for what we want to do when gradients are available. And then we'll go to, well, when gradients are not available, we still want to do all of these things. And so how do we actually set that up? Okay, I was told by my group today that now the problem makes sense. So I think it was a very successful day 1 for us yesterday. Okay, very good. So let's take a quick recall. So our definition is our target density pi of x is proportional to e to the power minus u of x, and u of x is called the potential. And our goal is to be able to generate samples from this target distribution pi. And the way we do this is we propose, we either accept or reject, right? And so we run this iteratively. Conserving this particular acceptance probability, which then thereby ensures that we are targeting the correct distribution. And so really the key in actually designing an effective sampler is the choice of the proposal distribution. And what we did yesterday is we use random walk metropolis, which was just normal x comma some h with some maybe diagonal covariance structure if I'm in multiple dimensions. And this is exactly what we did, right? But now today what we'll ask is, okay, can we get better Markov chains if we use more information about my target density pi in the proposal distribution? So can we use the gradient of log pi, which is nothing but minus negative of the gradient of the potential, to make smarter proposals? This is at least going to be the question, and then obviously the answer will be yes, we can actually use this. And one of the reasons this might help is, and we'll see a visualization soon, is that what's going to happen is we are going to encourage proposals closer to area of high probability by telling the algorithm, look, the gradient points in this direction, go propose in that direction, right? And in that way, we want to hopefully reduce the number of rejections that happen, and then thereby increase how well the Markov chain moves in my state space, which is essentially called mixing. So the most popular way to employ gradients in a proposal is the Mala proposal, which is the metropolis adjusted Langevin algorithm. We'll see the origin story of this algorithm in a couple of slides, but this is the proposal itself. So y is xk plus h pi 2 grad log pi. This is nothing but negative u plus a normal with variance h. And this is equivalently saying that the proposal is a normal x minus h pi 2 grad u of and variance h. So it's very similar to a random walk, except I've put in basically an additional drift that says move in the direction where the gradient wants you to go. So this looks something like that. I have my target density, which is normal 0, 1. And if I'm currently at the state -3, the previous random walk proposal is in the orange over here, symmetric around my current state. But then the Mala proposal looks at the gradient here, and it's a positive gradient, or U has a negative gradient. And so it moves more in this direction, right? So the blue is the Mala proposal, right? And so what's going to happen is I'm then going to be able to propose more in this area of high probability, and that is more likely to be accepted. And so the average jump size is going to be much larger, right? Because the average jump size is roughly this, whereas the average jump size is going to be roughly this much in random walk, which would be smaller, right? Okay. So that's a pictorial explanation of why they help. There's also a way to summarize this mathematically. And one way, which is sort of in the study of MCMC historically been the way to do it, but things have changed recently. But one way to do it is by establishing some optimal scaling results, which is to ask, well, how should H, my proposal variance, and the term in the drift be tuned? So I have two H's. Sorry, I'm going to go back. In the random walk, I have an H, which is my variance in my proposal. So how wide do I want the variance to be? And in the Mala, I also have H here, but this H is the same H that goes next to the gradient. But it's the same H as the step size, the variance. And so how much do I want it to be? And so Roberts and Rosenthal in 1998, and then this is in 2001, showed, well, an optimal step size under various conditions of what kind of target density, it's roughly a simplified assumption, scales of the order of 1 by d, where d is dimension. Right? So as dimension increases, your random walk variance should scale down linearly. Okay? And there's a constant next to it as well. And then here for Mala, they showed it should be d to the power minus 1 by 3. So that's not such a large reduction in the variance, which means that as dimension increases, I will allow myself to still make slightly larger proposal moves than I would do in random walk. Right? What's sort of also neat is, irrespective of what actual H star gets you, the optimal acceptance, because the constant next to it are sometimes difficult to actually obtain practically, is that the optimal acceptance rate of the algorithm at that value of H star was shown to be roughly 0.234. And this is often called like the magic number in MCMC. It shows up in various places. But for Mala, which is a different proposal, the optimal acceptance is 0.574, which is a higher acceptance. Okay? And so this actually really helps in practical tuning of the algorithm. So if you're given a target density and you know roughly if my dimension is, let's say, 1,000-dimensional problem, you know roughly if I'm using random walk, then the variance should be roughly something by 1,000. So it'll probably be a very small variance in the proposal. But what is the actual constant next to it? Sometimes we wouldn't know. But as a practitioner, what you can do is you can run the algorithm, warm up the algorithm a couple of times, and track on average how many acceptances do you get, right? And you increase H and you decrease H, and then you track, well, what happens with these acceptances? And when you get about 23% acceptance, that's sort of the optimal acceptance. So that H is the H you set it to, right? At least in the practical setting. Okay. Okay, so where does Mala actually come from? Because it's called Metropolis Adjusted Langevin algorithm, so it might have something to do with Langevin diffusions. And it does. So the Mala algorithm is motivated by the continuous time stochastic process, the SDE. In this paper by Gareth and Richard Tweedy, sort of lays out the Mala algorithm and its origin story. So if you look at the overdamped Langevin diffusion, which is this SDE over here, so LT is your SDE, and then WT is your d-dimensional standard Brownian motion, and the drift is 1/2 grad log pi. Right? If I look at this, then the key property of this is under mild conditions on pi, which involves some Lipschitz conditions, this diffusion has pi as its unique stationary distribution. So the philosophy then when building an algorithm was, well, okay, if we can run this continuous time diffusion, continuous time process, then as the process is going for a longer time, then I should be able to get samples from pi. There's a limiting argument here as well. Okay? But obviously this is in continuous time, and so that's not going to be possible for us to simulate anything on a computer in continuous time, which means it would require some sort of a discretization. Right? And that's exactly what gets us to the one stage of the Mala algorithm, is it says, okay, if I just do a simple discretization and set dt to h being the same h that I was talking about before, then that's exactly what I'm going to get when I do this. So if I set a step size of h, so dt is h, I get xk plus 1 is equal to xk plus h by 2 grad log pi xk, and a, because it's a Brownian motion, I get Gaussian updates. This is called the unadjusted Langevin algorithm. So what happens is you have the continuous time Langevin dynamics. We can't simulate it on a computer, so we discretize that dynamic, and then we get something that isn't quite going to be converging to pi, but it is discretized, and it will give us something reasonable. Right? It's also in machine learning, it's also called the Langevin Monte Carlo, and it's very popular in machine learning. The issue is, like I said, that there is a bias because I'm discretizing the stationary distribution of ULA, this unadjusted Langevin algorithm, is pi sub h. It depends on h. And there are various results that show that as h goes to 0, we get nice behavior in terms of convergence to pi. So the bias is order h, so vanishes at h as h goes to 0. But then if h is going to 0, then within a unit interval, I have more and more discretizations, more and more steps in my discretization. So I physically on a computer, I will not be able to let time evolve to infinity. I can let the discretization size evolve to infinity, but my unit interval will remain a unit interval. But I need pi sub the actual x sub t, or sorry, L sub t to actually converge to infinity, which won't be then possible practically. So there's a balance there. And so obviously, so now for a fixed h, EULA does not actually target pi, but targets pi h, and that's a problem. And so the solution in the Mala algorithm was then great. Well, we'll just use this as a proposal. Okay, we know that this does something reasonable. If h is small, this gives us a process that almost converges to pi. So if I just look at the right-hand side over here, the value that it gives me, I treat it as a proposal in my algorithm and then allow myself to accept or reject it. And that's called a metropolis correction of any approximate scheme. So we can build approximate schemes that sort of approximately converge to some approximation of pi, and then use that process or the next iterate of the process as a proposal in my metropolis Hastings algorithm. And that's a metropolis correction for any unadjusted algorithm. Right? So this is sort of the origin story of Mala. And so just a summary, we have ULA, which is, does it target pi exactly? No, Mala does target pi. This one does not require an MH correction, which is why it's biased. But this is also why it's very popular in machine learning, because an MH correction requires the evaluation of the ratios of the target density, which then can be quite burdensome if you have massive data sets, because you have to evaluate the likelihood or evaluate the whole data distribution at every sweep of the algorithm. And typically these samplers run for on the order of million iterations. And so that becomes really expensive to employ. So this is the fact that it doesn't require the correction is sometimes it's a positive or a negative depending on what your objective is. If our objective is to get quick solutions that may be slightly off, but they're quick, then this is a plus. And if our objective is to get correct solutions, even if it takes a while, then this is a plus. Right? Having correctness is a plus. Another important thing is that ULA requires only one gradient per iteration. And that's because we just need to evaluate a gradient and that's the next step, and then evaluate a gradient, and that's the next step. But here in Mala, we need to evaluate 2 gradients. Do we have guesses for why we require 2 gradients? Sorry. One is inside the normal when you're proposing, yes. Yeah, it's exactly, yeah. Sorry, I'm going to have to go back a bit. But when we evaluate the acceptance ratio, there's a qy comma x and qx comma y. The qx comma y is the actual gradient that we use to actually generate. But then we need the gradient at y as well to understand what's the likelihood I go back in time. And so it requires 2 gradients, which is annoying, again, to people dealing with these massive data sets. And so I sort of mentioned this in general. If the dimension is large and if the data set is very large that we're dealing with, ULA is often preferred. But if our interest is in targeting exactness, then Mala is preferred. And in the statistics and ML community, it's quite interesting that there's a very nice divide. This is ML and this is statistics. I don't know why. It's just the way it is. Okay, so we talked about yesterday about how to do sort of reasonable inference for our problem as well, in the sense that we run a sampler, we have an estimate maybe of some expectation, and then we want to be able to know, well, does this have a finite variance or not? And that requires us to ensure that we are actually converging to the target density at a reasonable enough rate. Right? And that meant that something like geometric ergodicity of my kernel is useful. And so for the Mala algorithm, Roberts and Tweedy first looked at some sort of concrete convergence results. Again, this is the same setup. So pi of x is e to the power minus u of x. And I'm going to highlight some of the conditions more carefully. But just to remind us what geometric ergodicity result is, so pi is the density on RD that is positive and continuous, and that the tails of pi are sufficiently light. So I'll talk about that in a second. Then there exists a h that is small enough, so a step size h that's small enough, that the Mala chain is geometrically ergodic in that it converges to pi at a geometric rate where rho is a number between 0 and 1, and your convergence can depend on where you actually started from. Right? So this is good because it says that, okay, there is a small enough h where if you don't go too crazy, if you don't increase h too much, we are guaranteed to have a Markov chain that converges strong enough to allow us for things like a central limit theorem, which is useful for practitioners to whom we are giving back these estimates. Okay, so what do I mean by sufficiently light? So let's take a look. So what are the tail conditions on pi? So the first thing is that the tails should not be too heavy. And this is actually true for both random walk and Mala. And specifically for large enough norm x, the gradient should diverge to infinity as x goes to infinity. So for example, if you look at a Gaussian function, a Gaussian PDF, the potential is nothing but a quadratic. On both ends, you have a gradient that's going to become a vertical line in the limit, which means that you have the gradient that's going to infinity. And that tells us that the tails are not too heavy. Right? But there is another disadvantage. I can't afford to have tails that are too light either. So if the tail is too light, which means that it is actually going to the gradient u of x is increasing much faster than the order of x itself. And if that happens, then the tails are too light. And so it should be that this goes to a positive constant. And under these two conditions on the tails, and the conditions are just essentially on the tails, there's one smaller condition that just says that your target density shouldn't basically have like these almost like these infinite rivets in the target where it just keeps going up and down in the tails of the distribution as well. But if you have some sort of reasonable smoothness after some like some R region or epsilon region around a mode. And then in the tails, if you have these two conditions, then you're good. Right, so one of the interpretations is the gradient must grow fast enough to pull back the chain into an area of high probability, so that the gradient is actually giving us information that go there where the high mode is. But it should not be so fast that it actually overshoots and goes past the mode. And I'll show you an example of that. I should have put that on the next slide. So keep this in mind. I'm going to show you a plot addressing this point here, that I don't want gradients to grow too fast as well. Okay, just a quick note on how some of these results are shown. The actual technical proof, I put a reference, but at least the idea of how do you show geometric ergodicity, one way to show it. There's multiple ways of showing it. So one way of showing a geometric ergodicity is that you can show, if you can show that the Markov kernel exhibits a spectral gap, and that's a sufficient condition. Sometimes it's a bit challenging in continuous state spaces to actually show that condition, because you may not have a continuous spectrum, and to be able to then estimate or say something about the eigenvalues is a bit challenging in the general state spaces. And so instead, a way to show it that's often used is drift and minorization, which is essentially a Lyapunov condition and a minorization. So we'll discuss some of that. So let's look at the drift condition. So a drift condition says that you have a kernel P, but now let's suppose I have a function V, which is the Lyapunov function, also called the drift function, so that PV, so PV is nothing but the expected update on V in one iteration of the Markov chain. PV is less than equal to lambda V plus B, indicator of some set C. So C is some set in X that's going to be called the small set. And so here's the interpretation. So outside the set C, so if I'm not in the small set, if I'm somewhere else, then this indicator function goes away. And what this says is that on average, I'm going to go drift downwards on the set V. Right? So outside the set C, V decreases on average. This will imply that the chain will be pulled back towards the set C. But if I am in the set C, if I am inside, then the chain should be allowed to diverge away, maybe not too much, but should be allowed to diverge away. And that ensures that I go out of the set C enough times and back in the set C enough times. Yeah. Not necessarily, because, for example, if the whole space is small, then I get uniform ergodicity. Okay, yes. So C is often going to be a compact set. So if so that's true. So if my whole space is bound, if my whole space is small, as in if C is all of script X, then the Markov chain is uniformly ergodic. So I don't necessarily get the M of X, but that. No, actually, C is it's possible. No, so C can be unbounded as well. So maybe the next slide might shed some light, because C connects back to the minorization condition. Okay, so this sort of tells us something about, in one iteration, I want the function to drift down towards C if it's not in C, and if we are in C, it's happy to move away from C. Then the minorization says the following: there exists a C, which is the same C from the drift condition, such that a probability measure nu holes on X and epsilon goes to 0 exists such that I get Px comma A is greater than equal to epsilon times nu of A. And this must hold for all X in C and for all nice sets A, right? And if I have a minorization like this, then here's what we get. What we get is, once I'm back inside C, then because I can write it like this, with probability epsilon, I'm going to be able to draw from the measure nu. And that's akin to actually drawing P. So with probability epsilon, I draw from the measure nu. With probability 1 minus epsilon, I draw from whatever is remaining in the greater than equal to. So what this allows us to do with drift and minorization, we get the following, that the chain returns to C from anywhere, that's the drift, that on average, I'm going to get a decrease in the drift function. So on average, I'm going to drift down to the set C. Once I'm in C, with probability epsilon, the chain has a chance of forgetting my starting value because it will draw from nu. Right? Which means that now I have an instance with probability epsilon. If I'm in the set C, I forget my current state. Right? And then that tells me that, okay, now I have no sort of conditional no independence on the previous state. Right? And that's sort of at least, so obviously when we're running this, we don't run the algorithm like this, but in order to show the proof, we show that this can happen. And together, this will imply exponential convergence to phi in total variation distance. So for Mala and for other kernels as well, but there's a couple of papers that sort of hack at showing geometric ergodicity for the Mala algorithm. And the main challenge is establishing the drift condition and establishing something like this. And you sort of have to come up with functions V that allow you to do this. Because the drift function is not unique. And so there's a particular function, and I'm happy to talk about it later, that's often used in some of these proofs. Okay, so we know that that's the result. So now the question is for what kind of distributions are these tail behaviors satisfied? Right? So because we showed a couple of tail behaviors, it shouldn't increase too much, but it should not increase too less either. So this family of distributions is often studied because it allows us to study tail behavior in different ways. And so we look at e to the power minus absolute value of x to the power beta. And so this allows us to have different types of tail behavior. And the gradient for this is beta times x to the power beta minus 1 sine of x. So now I should mention that now I'm just assuming I'm on R and not RD, just to make some calculations easy for us. So if I focus just on this family to try and understand when do I have good rates, well, when beta is greater than 2, then this corresponds to super Gaussian tails because this is greater than 2, so 2 minus, so something like 4, 4 minus 1 is 3, so now my gradients are increasing at a cubic rate, right? So this is lighter than Gaussian tails. Beta equals 2 is obviously Gaussian, right? Gaussian tails. Between 1 and 2, I have sub-exponential tails, so these are heavier than Gaussian, but not too heavy. And then beta equals 1 is the actual Laplace. That's the Laplace distribution or the double exponential distribution. And beta between 0, 1, I have very heavy tails. And also, I'm no longer lock concave either. So that's another issue. And so for these sort of categories, I have different ways at which the gradient increases. So for beta greater than 2, it's super linear. For beta equals 2, the gradient is linear, and then it's sublinear for beta less than 2, right? So now this is like a summary of the results for geometric ergodicity for this family. If I have super Gaussian tails, as in beta is greater than 2, then I cannot be geometrically ergodic. And it's not that the sufficient conditions don't hold. I can provably not be geometrically ergodic. Right? If beta is 2, so if I have Gaussian target, then I can be geometrically ergodic, but I need to ensure that h is not too large. And there's a relationship with the Lipschitz constant as to how much h can be. If I'm sub-Gaussian, then I'm between 1 and 2, or beta is 1. In both cases, I'm definitely going to be geometrically ergodic. But if I have heavy tails, beta between 0 and 1, then again, I'm provably actually not geometrically ergodic. And not that the sufficient conditions don't hold. Again, it's provably not geometrically ergodic. So what's happening at least this one is, so when I have too heavy tails, basically the gradient doesn't give me enough information. So if I'm too off in the tails, and if I have very heavy tails, there's a lot of mass there locally. So the algorithm doesn't know it should actually move here where there's a lot more mass, right? It should move more closer and far away. because locally the tails are so heavy, it feels like there's a lot of mass out in the tails. But if I'm super Gaussian, the problem is my gradient increases too quickly. So here's the plot. So if I have e to the power minus x to the power 4, that's my target. So it looks something like this. So it's like a better bowl compared to a Gaussian. And this was my random walk. There is Mala I've plotted, but Mala is somewhere here, right? Because the gradient is too massive, right? If I were to just start somewhere locally, if this red dot was somewhere here, the Mala proposal wouldn't look so bad. But then often I don't know where an area of high probability is. And so I just start somewhere. I should be able to drift back. But in this case, if I start from here, my Mala proposal is centered at 80 or something like that. Okay. So just a last comment, and that it's not that the case that that gradient-based proposals are always better. So, for example, for the super Gaussian case, when I have very thin tails, random walk is also provably geometrically ergodic. And it's not geometrically ergodic only for heavy tails, which is also true for Mala. But Mala is not geometrically ergodic when your tails are way too light, right? So from the table itself, one would naturally think that, wait a minute, this means that random walk is the better algorithm to use because it works in a larger subset of cases. Okay? But of course, geometric ergodicity is a qualitative statement. Of course, it is quantitative as well, but it sort of says that you converge at a fast enough rate that you don't have to worry about some of the core conditions holding true. But there's other results on sort of non-asymptotic rates, which are also can be very, very useful. Okay. So we'll discuss some literature on non-asymptotic time mixing time bounds. And this is sort of, there's like new work that comes out every couple of months in this area. And new proof techniques that come out. So I'm sort of catching up to some of this as well. But the key question in the non-asymptotic mixing time bounds is to say, after t iterations, how close am I going to be to the target density? And I don't want to do this as n goes to infinity or anything like that. I want a bound that's a function of my parameters that I'm dealing with and the time t. And so typically, we want to bound some framework of the distance, maybe mu t comma p. So mu t is like I should have mentioned, mu t is the distribution of xt, so marginal distribution after time t. And pi is my target density, and the distance could be KL divergence, total variation, or Wasserstein distances. But at least the work I've seen so far, and I've looked at so far, I've mostly looked at total variation distances, because then it allows us to more easily compare with the more traditional literature that's out there in TV distances. And then epsilon here is the desired accuracy. So the question is, how long will I take? What t will I take so that the TV distance is less than equal to some epsilon? And so obviously the result would be a function of epsilon, right? So the mixing time bound is the smallest value of t such that this holds. And so the bounds that one gets are explicit explicitly dependent on the dimension d of the problem, very similar to the scaling results we discussed earlier. It's also dependent on the condition number of the problem, and I'll talk a little bit more about what L and M are as well. And then epsilon obviously is how accurate do I want to be, because if epsilon is small, t will obviously need to be then large. So here's a summary of some of these results. So the first condition is often the framework is we assume that the target density is such that the potential is L smooth and M strongly convex. So L smooth implies that the gradient does not increase at a faster rate than linear, essentially, right? So we have L Lipschitzness of the gradient, and this ensures, at least for the Mala algorithm, that the Euler discretization is controlled, because if this doesn't hold, then the Euler discretization itself is going to be a problem. And then there's also an inherent understanding that H then has to be on the order of and not much greater than 1 by L, because if it's much more than that, then that, but much more than 1 by the Lipschitz constant, then your discretizer will break down as well. And so you could try that. You take simulating from a Gaussian and run the discretized algorithm, but set the step size h to be, let's say, 10 or something massive, much more than what the Lipschitz constant allows. And you'll see the code give you NAs immediately because it just shoots up. The discretization is too much for it to give you something reasonable. We also require M strong convexity, which basically means that my function is convex, but it's so convex that I can take away an M order quadratic and it's still going to be convex. That's essentially M convexity. And then as a consequence of these two, we look at the condition number, which is L by M. So for a Gaussian, for example, this is essentially the ratio of the smallest to the largest to the smallest eigenvalues. So it tells you basically how well conditioned the target density is. And so roughly speaking, people study the mixing time of ULA, MALA, and they also study mixing time of another algorithm called HMC. But for the ULA algorithm, there's a couple more references here, but this one was like the first primary one. The mixing time is shown to be kappa d pi epsilon squared, because there's going to be a bias that will remain. MALA is kappa square root d. So that actually shows that this is fairly much, in some way, faster than ULA. And that's because of that accept reject. But one of the main things here that's sort of interesting in the literature is that the optimal scaling literature that sort of studied mixing time, not mixing time, but studied convergence under certain conditions, actually we got a 1/3 rate. And so the mixing time results here haven't actually reached the 1/3 rate, even under like more and more conditions. We've only been able to go to d to the power 1/2. And so it's, at least to me, it's unclear why there remains to be a mismatch. But what's very interesting is that this literature doesn't ever cite or talk about that literature. And that literature has basically also never really, so they just don't communicate with each other. Okay, I wanted to just make sure we end with again, some context setting, because for the kind of problems we work in, we want to ensure any condition we have and things are actually useful to the Bayesian practitioner who might come to us with this problem, right, of running a sampler. So one of the most popular models, and we'll pick this up also again in like the non-differentiable part on Thursday, is a logistic regression or a Bayesian version of the logistic regression model. How many of us know what a logistic regression model is? Some of us. Oh, that's very good. Okay. So essentially, now I'm talking about real data. So this is not on a computer right now. Eventually, we'll move to a computer. But real data, I have yi's, for each observation I have a label of a success or a failure. Did a student pass or fail? Did somebody get cured or not get cured, or whatever the data set might be? And some covariates are basically demographic information on these people, some sort of information that's important to understand whether the student passed or failed. And then in order to model this relationship, what logistic regression does is it says, I'm going to model the probability that any yi equals 1, given its set of features, is just 1 by 1 plus e to the power minus xi transpose beta. So this number is a number between 0 and 1 and has certain properties as x increases and x decreases and so on. So this is a kind of model one assumes. And this gives us a likelihood function that tells us, well, you know, what are likely values of beta as a consequence of having observed a series of ones and zeros. But because this is a Bayesian model, and the goal is here to now estimate beta, understand what beta is, so that we have an understanding of what sort of weights are associated with each of the covariates, and that allows us to predict for a new individual what is the probability that they will pass or fail the exam or something like that, right? And so a prior that one can impose, and I've just done something here, I've imposed a Gaussian prior, which is very common. So that means that I'm assuming before the data starts, before seeing the data, I have a feeling that betas are basically all useless, that none of the covariates are important, so convince me that they're important, and maybe sigma square is some variance that I've chosen. And so using this, I can write down the posterior density and the potential of the posterior density as well, using my Bayes theorem and then exponentiating things and etc. And I get this as a consequence of my likelihood, and this as a consequence of my prior. Right? So this becomes my potential, and this is what we would then write up in code. We would also take a gradient of this to see what the gradient looks like. Right? So the gradient for this looks now something like this. So this is going to be now a p-dimensional vector. Now, by looking at the gradient, I'm going to find, well, this is just a linear term, and this is a sigmoid over here. So what I get is the smoothness L for the L smooth part is 1/4, the maximum eigenvalue of what's called the X transpose X, the model matrix formulation. So the largest eigenvalue of X transpose X plus 1 by sigma squared. So this sort of 1 by sigma squared over here allows us to bring in some sort of better conditioning in your function. Right? So that's the L smoothness constant. And then what's interesting is that the Bayesian likelihood, the logistic likelihood is not M strongly convex. So it's convex, but it's not so strongly convex. And that's again because of the sigmoid function. But what's neat is that because we have the sum of two functions, this is strongly convex because it has a constant 1 by 2 sigma squared next to it. And so M is 1 by sigma squared dot. Sigma squared is 0. So this is only from the prior, and the likelihood is only contributes greater than or equal to 0. Great. So this is I wanted to show this only because this is one of the most popular models some of these papers sit down with, because it's sort of straightforward to see that it satisfies some of these conditions, but also it's actually used fairly often when we're trying to build when we're doing classification problems. Okay. And then the condition number for this kappa is L by M. So if I have a model matrix that has a very large eigenvalue, then my Markov chain will mix slower no matter which one I choose, ULA or MALA, because it is order kappa. Right? So if kappa is large, my Markov chain will take more time to move. And this is also why people say, well, you should standardize your covariates when you have data, you should center and scale them, and so on, because it improves the condition number. Okay, so we know all regularity conditions are satisfied, and so for just some very toy simulated data, what I just did is I simulated some data, I put this prior, I have this potential, I have the gradient, I can run both random walk metropolis and I can run MALA as well, and just to see what some of these MCMC output plots look like. So this is not very helpful, I realize, but at least in the trace plot, this is, I set P equals to 2, which means I had 2 covariates. And so for both of them, I can sort of see the evolution in 1,000 steps of how the Markov chain progresses. The random walk does not move as well as the MALA, but it's very difficult to see here. And it's in general very difficult to see with trace plots, because these are sometimes much longer trace plots. But what we can do is look at what are called autocorrelation plots. So this basically estimates the autocorrelation at various lags. So how much dependence remains after 10 lags, 20 lags, 30 lags, 40 lags, and so on. And so for this, I forgot the legend here, but it's the same legend. So for both components, random walk, it's not bad actually, but the dimension is only 2. So where random walk will fail or not do very well is if I'm in very high dimensions, because at least the optimal scaling literature tells me that it's about 1 by d in terms of scaling. So I'm going to make very tiny moves. For d equals 2, for dimension equals 2, it's not that much of a problem. But even still, MALA seems to have much lower correlation, which is a good thing in my MCMC. That means I'm mixing better. Right? Okay, I'm just going to wrap things up. So that was MALA, but MALA is sort of like the first entry point to gradient-based MCMC methods, but there's a lot more out there. And this list I'm going to show you is very non-exhaustive. But one of the main really popular ones is Hamiltonian Monte Carlo, and it comes from Hamiltonian dynamics, but it can be viewed as multiple steps of MALA in one step of a Metropolis Hastings algorithm. This is a very crude viewpoint, but think of I use one gradient, and then I use another gradient, and then I use another gradient. And when I do, let's say, 10 gradients, wherever I end up, that's my proposed point. Right? But if we do it in a particular way, it becomes the Hamiltonian Monte Carlo algorithm. And this is, the mixing for this is kappa square root kappa square root d. So there is a square root kappa improvement. So it's a little bit more robust to ill conditioning than Mala. There's also Barker's proposal, it's called Barker MCMC. And this one's much better for super linear gradient functions, so something like super Gaussian, when beta is greater than 2. Also, far more robust if you're doing a discretized version with no adjustment. It's far more robust. It will almost never give you NAs when you run the algorithm. It's going to keep things fairly robust. And similarly, there's tamed Mala, which does something similar. And both of these can essentially be viewed as different discretizations of the original Langevin SDE. So you take the Langevin SDE, and instead of doing an Euler discretization, you do a different discretization, and that gives you possibly a different proposal, and then you put that in the MH algorithm and then do a accept reject. There's second order methods as well. So these are generally called Riemannian. For some reason, they're also called manifold, although they're almost always run on RD. Mala and HMC. So here the idea is that I'm going to allow for, at every state, I'm going to allow a different curvature locally. So instead of just taking the information of the gradient, I'm also going to take information locally of the Hessian as well. Right? And that's going to tell me what the curvature is, what that particular local structure looks like. Naturally, this is a far more expensive algorithm because you have to calculate Hessians in every step. And then another very popular sort of extension of all of these, including Mala, are then stochastic gradient implementations that say, okay, well, you have all of these gradients you have to evaluate every single time, but my data set is massive. And so I do not have the luxury of evaluating these expensive gradients. And so what we do is we can say, okay, well, I'm just going to randomly choose a subset of my data points every single time and evaluate the gradients on those subset of the data points. And that gives me a stochastic gradient algorithm that still has some biasness because I'm not using all of the gradients. And then there's some techniques that we do to ensure that the step size goes to 0 at a certain rate to ensure that at least I'm asymptotically unbiased. Okay, that's about it. And so the next part 3, we'll discuss, okay, all of these results are good and interesting, and Mala can be pretty decent, but we would like to be able to extend it to situations when I don't have differentiability. Thank you.
Thank you, Dootika.
Thanks.
Questions?
We're hungry.
Your kappa d by epsilon squared in one of the slides.
The ULA?
Yeah, what is the epsilon there?
The epsilon is the TV, the distance to TV distance. Yeah, that's it.
And the graphs, what are you plotting?
So this is the estimated, this one?
The previous one.
This is just the raw samples.
Of y, is it?
No, of the beta. So
Beta.
the posterior is on beta.
On beta.
So we run the 2-dimensional Markov chain, Metropolis Hastings algorithm, both random walk and Mala. And this is beta 1 and this is beta 2. Sorry, I should have had the top things on.
Okay. Okay, thank you. Yeah, now you have a... Yeah.
Okay, I have 3 quick announcements to make. On the WhatsApp group, I've sent you all the rooms you're going to meet in. For some of you, they are different from yesterday. For some groups, maybe a light on the board is probably easier than